So this is a generalization of the estimation function. Okay, so we'll start. So in least square regression, the estimation function. Do you know what is the estimation function? The estimation function is nothing but y cap x. That was w0 plus w1 x yesterday. Okay. So the y cap x, okay, or the estimation function in general, it is important now, is, or you can say must be a linear combination, okay, must be a linear combination of basis functions. What are basis functions? Have you understood what is a basis? Do you know what is a basis? Anyone? How many of you know what is a basis? In linear algebra concept, what is a basis? You don't. Okay. Anyway, I'll give you an example. Okay. Bases are like the very important quantities, very basic and important quantities, but they are used everywhere. With them only you can construct bigger things. Okay, those are the bases. Okay. For example, in your coordinate system, you have your coordinate system, right? X, Y, Z, X, Y, Z, right? Coordinate system. Now, if I tell you that, yes, this is the point where the aeroplane is. This is the point where the aeroplane is, right? This is the point where the aeroplane is. Fine. Then give me the coordinates of the aeroplane. Then how will you do? Aeroplane is flying on sky and it is in a three-dimensional space. So it has X, Y, and Z coordinates, right? So what you will do, yes, find the X coordinate, find the vector to that, and that is the vector, right? You can also find which direction it is in your coordinate axis, which direction it is. You can also say from the ground level how much distance it is. Because a vector consists of both direction and magnitude, isn't it? Direction and magnitude, right? So therefore, how you will write this vector? For example, you must have seen in your class 12th days that this can be written as something like 3 I cap, 4 j cap plus 5 k cap. Do you remember that? How many of you remember that? Most of you, I think. Okay. What does this mean? It means on x-axis, it has 3 units. On y-axis, it has 4 units. On x-axis, it has 5 units. Right? So you wrote the vector v of the aeroplane A in terms of 3 I cap plus 4 j cap plus 5 k cap. Right? What does that mean? It means that you have written the vector VA in terms of the basis I cap, j cap, k cap. You got that idea? So therefore your basis elements here are these. These are known as the basis. So I cap, where is I cap? I cap is on the x-axis. So your x-axis direction is one basis. What is j cap? Y cap, y direction. So j cap is one basis. And z k cap. So this is another basis. So any vector in a three-dimensional space, you can only write it using I cap, j cap, k. So therefore, it depends on the basis I cap, j cap, k cap, right? So therefore, these are known as the basis. You got that idea. So therefore, these are known as the basis. Okay. Now, any polynomial, you can write them as a linear combination of constant x square, x cube, x fourth, and all powers. So therefore, those are the basis elements. Because you can write any polynomial using those. Is the basis idea clear? So what is a basis? Basis is something which you can use to write anything more generalized. Those are the very basic elements. Basis. Okay. But there is one property of the basis. Okay. That means it should be linearly independent. Okay. Have anyone learned about linear independent things in linear algebra and bachelor's? Yes. Okay. We will come to that. No, don't worry. linear combination of basis functions. This much you should have in mind, that in least square regression, the estimation function y cap of x must be a linear combination of basis functions. Okay, what do I mean by that? Okay, so therefore that is you need to have, okay, y cap of x is equal to some summation, or maybe I can write for the first time in a easier way, alpha 1 some f1 of x plus alpha 2 f2 of x, alpha 3 f3 of x, so on, maybe till n, alpha n fn of x. So here your basis functions, basis functions are f1x, f2x, so on up to fnx. These are your basis functions. You got the idea. So we are writing as a linear combination of basis functions. Can you see why it is called as a linear combination? Okay, you know what is a linear combination, right? Alpha 1 times one basis plus alpha 2 times another basis function, so on. Okay, now, okay, so and alpha i's are referred to as parameters of the estimation function. Parameters of the estimation function. Okay. And second property is, one of the most important property is, each basis function fi of x must be linearly independent, okay, from the others. Now, what do I mean by that? Okay, so linear combination of basis functions are said to be linearly independent if this condition happens. Suppose C1 F1 of x plus C2 F2 of x plus so on Cn Fn of x is equal to 0. Suppose, and if your F1x, F2x, so on up to Fnx are linearly independent, and you have this condition 1, then that implies that C1 equal to C2 equal to up to so on equal to Cn equal to 0. What it tells you? What from what you understood? You cannot write any basis functions in terms of another basis function. I mean, linearly independent means f1 of x is not equal to k times some f3 of x. You cannot have it. Okay. You got that idea, no? You cannot write one basis function in terms as a multiple of others. So therefore, if C1 f1x plus C2 f2x is 0, you can easily write, no, from here what we will do, f1 of x is equal to minus of C2 f2, C3 f3, so on Cn fn divided by C1. You can easily write f1 of x in terms of others, right? But linear independent doesn't mean that. Linear independent means you cannot write in terms of others. So therefore, it will force all the constant to be 0. In that way only you can prevent that from happening. If you set the ci's to be 0, in that way only you can prevent one function being written in terms of others. You got the logic? Okay, you got the logic, right? Okay. Anyway, so this is what I mean, that your basis functions should be linearly independent. Okay, and this is the condition of linearly independent. This is the condition for linear independence. Okay, if each basis function is linearly independent, then the linear combination is equal to 0. That means all coefficients are equal to 0. Good. So now let us enumerate the data points. Okay, let us enumerate the data points. How many data points we have? Okay, how many data points we have? So enumerate data at each xi. At each xi, enumerate the data. What do I mean by that? So the estimation function y of x at x1, y cap at x1 is equal to, yes, can you follow this? Oh no. Can you follow this? Can you follow the green ones? Using the green ones, y cap at x1 we can write as alpha 1 f1 x1 plus alpha 2 f2 x1. Yes. So on alpha n fn x1. Okay. Now can we write similarly y cap of x2 alpha 1 f1 of, yes, plus alpha 2 plus alpha n fn x2. Yes. So like that, can we write how many data points we have? Suppose we have data points, m data points, m. We have m data points. And how many basis functions we have? N basis functions. So we have, I will write here, we have m data points and we have n basis functions. There is no reason for m and n to be same. They can be different, right? They can be different. There is no, a reason why m and n should be equal. The number of data points should be equal to the number of basis functions. There is nothing, no rule like that. So we have taken m and n to make a general statement here, to make it more general, to make the working procedure more general. Okay. So what I should write the last data point? Y cap of x m equal to alpha 1 f1 of, yes, plus alpha 2, yes, so on alpha n fn, yes. So you got the idea. Now you can see why linear algebra will come to picture, because this is a set of system of linear equations. I mean, not linear equations, f1 f2 can be non-linear. Okay, I mean system of equations. Okay, now this is very difficult to write it always. Can we pack them in matrix? If you have so many things, pack them in terms of matrix, right? Can we pack them in terms of matrices? How we can pack them? Okay, so here is the catch. We can define, okay, we can define, so this is now the matrix. Define x vector, okay, belong to Rn, okay, and Rn are the basis functions, okay. Okay. Anyway, think of x as Rn and take y cap, capital Y cap, which stores all y hat xi, okay. Yes, all y hat xi. Any issues? Why? No, why it should be? I mean, see, data points, you can have 10,000, 50,000 data points. But the basis functions, if you're considering a particular problem, for example, I can say, which example I can say? For example, sin x, you are dealing with AC current. I mean, suppose you think that, you know, AC current is sinusoidal, right? AC current which we are plugging now, AC current, that is AC current, no? It is a sinusoidal wave, right? AC current is a sinusoidal wave. Yes. Yeah. So how you represent sinusoidal wave? I hope you remember the expression of sinusoidal, no? X minus x cube by 3 factorial plus x fifth by 5 factorial, like that. Expansion of sin x as higher order. Taylor series expansion, right? So those are the basis functions there, x cube, x fifth, and all, right? But you can have high number of data, you can have 10,000 data, but those are the basis functions. Those are the basis functions. So there is no, I mean, a rule saying that the number of data points should be equal to the number of basis functions. We will see by doing an example. We'll see by doing an example, then you can appreciate it much better, I think. We will do that example, that social media and brain rot. That example we will do in the class. Okay. But let us formulate how we will solve that regression problem. Okay. I mean, it is a very nice concept, and it is building towards formulating pseudo inverse. Penrose generalized pseudo inverse, which I think you might be seeing in machine learning, I don't know. But already you are seeing in RC, reservoir computing, because that A transpose A then whole plus I inverse, that is like a pseudo inverse. Okay, those who are doing RC, they might know better. Okay. Okay, y cap is stores all y cap. Okay. And we can construct another vector beta, okay, which stores all coefficients, stores alpha is. Okay, stores all alpha is. Fine. Now, can you see that? Can you see that? And is there anything else we are missing? Y cap, we store all y cap. Beta will store all alpha is. What else is remaining? Yes, functions. Yes. So that we will store in a matrix A. Store all f I x j. F I x j. Because you see f2 xm is also there, no? F2 x2, F2 xm, Fn xm. So all these data are there. That we can store as a matrix. Okay. And what should be the size of the matrix? It should be a m cross n. It should be a m cross n. M rows, n columns. You can see yn columns. F1, F2, so on, n. But there are m number of rows. M number of rows. Is it clear? M rows and columns. Why it is the case? Okay. Okay. Now, can we write this whole equation? Then, using these ideas, we can write this whole equation. Okay. We can write this whole equation in terms of y cap equals to a beta. Is it okay? Y cap equals to AB. Yeah. Here. You'll fall there. Come. Y cap equals to A beta. Is it correct? How many of you can see? So what I'm trying to do here is write like this. That is y cap of x1, y cap of x2, so on up to y cap of xm. Okay. This vector is equal to f1 x1, okay, f2 x1, fn x1, then f1 x2, fn x2, f1 xm, fn of xm. Then beta is nothing but alpha 1, alpha 2, alpha 3, so on up to alpha n. Can you see? So if you have to multiply, what you do? Take this guy, multiply with this guy. So you will get this guy. So you can see that, yes, you can write it as y cap equals to a beta. Agree. Okay. So you see how we transformed the whole complicated set of system of equations into just one liner, that is y cap equals to a beta. Now we have to study about this matrix equation, y cap equals to a beta. Yes. Okay. Good. So can you, for simple example, like to just give you, it might look very abstract now, but to give you an example, a physical example, you might be knowing spring also, spring. spring, right? Spring. In class 12th, you might have, those who have taken physics as their subject, they might be knowing spring constant. Spring constant, right? What is the stretchness? Stretchness of the spring. So if you have the spring, okay, if you have the spring, then what will happen? So, and you have a block here, okay, and this is the wall. Yes, this is the wall, right? So the force exerted by the spring is nothing but F equals to Kx. Is the distance x you stretch the spring, and K is the spring constant. Okay. So this is the force, and that you can see that this F, you can actually write it as a basis function. Here F1 is x and alpha 1 is K. You understood, no? Just I am giving you a example here. Alpha 1 is K here and F1 is X here. And F is nothing but like Y hat. I mean, if you want to determine the spring constant of the spring. Okay. So this is just a bit of idea so that it doesn't appear that complex. Okay. So, okay. Let us be back. Let us, now we will use something known as a geometric interpretation. Okay. So, how can we explain next is? Now, this is the y cap is the estimation function. Do you agree? Estimation. I mean, it is not the, it will estimate. It will estimate. It is not the correct one. It is not the true data set. But there is a true data set, right? And what we want actually, our estimation should be as close to the true data set. Yes. So the true data set we can mark as y. This is a column vector. This is a column vector such that yi equals to yi is the data set. Is it okay? Then what is our aim? Our aim is make yi cap as much close to yi. Do you agree? Because yi cap is the estimation, no? Through regression. And yi is the real data set. xi, yi is the given data set, no? Is everyone understanding this part? What is yi? It's your given data set. What is your data set? xi, yi. How many times? I equal to 1 to m. These are given data set. What is yi cap? It's a regression. It's a regression, estimation. It's the estimation. How many of you understood? How much low I can go? Okay, understood. Understood. Okay, fine. So you understood this part, what we are trying to do here. Okay. Now let us understand this geometrically. Okay. Let us understand this geometrically. Okay. So you have, so yi given data set may be this one. Okay. Maybe this is y. This is the vector y. Okay. Maybe this is your regression. This is your regression. This is your regression vector. That is y cap. Okay. Equal to y cap equal to one more chance. Yeah. Y cap equal to should be 20. Yes, AB. It is your estimation curve. Okay, it's your estimation, like it's a regression. And what is Y? Y is the real data set. What is your idea? Your idea is to make the vector Y and Y cap as close as possible. Then only you will have the best fit. Then only you will have the best fit. Now, how can you do that? How can you achieve that? How can you achieve that? How can I make the distance between them smaller? Yes, we can minimize it. We can minimize it. Right? So, okay. So what is our aim? Let me write my aim here. What is the aim? Make y and y cap as close as possible. Do you agree? So, and the error is E and it is the L2 norm. Okay. L2 norm, that is y cap minus y2. This is L2 norm. I mean, it's just square root of that squared and all. Okay. Usually in regression, it's a distance between them. Okay. This is the error term. Okay. Now, when it can be? Now you tell me when can y cap it can be closest to y. The closest distance is when it will be perpendicular to it. Perpendicular. This distance is the smallest distance. Perpendicular. Any other distance you take will be greater than that. Isn't it? Any other distance, this distance you take, blue is greater than green. This distance you take, blue is greater than green. This distance, blue greater than green. Any distance you take is greater. Only the perpendicular distance is such that it will be the smallest distance between y and between the given data y vector and estimation function y cap. Agree? Now when can, now this y and y cap are vectors. Now when can, how can we say this perpendicular thing? How can we write this perpendicular thing? We understood that we have to take the perpendicular, but how we can give a condition to it? How we can give a condition to it? So use your vector knowledge, use your vector concept. This is, I will, okay. This vector is y, black vector is y, green vector is y cap. Do you agree? Now what is this vector? Can you apply vector law of addition? Resultant vector. Do you remember resultant vector? You don't remember. Okay, I will tell you the trick. I don't know whether you have gone through the trick, but it's usually the case. Go like this, form a triangle. Form a triangle. Go like this. Okay, write y. Then go like this, write something x. Okay, then go like this, but it should be opposite direction. So that should be in the equal to term. That is y cap. So then x is nothing but y cap minus y. So this x vector, this is the x vector we took, no? This is nothing but y cap minus y. Okay. Agree. So that is that y cap minus y term. Okay. Now what you want? You want what you want? Hmm? Is it clear? Can you think what we can do next? We have found all vectors. What can we do next? The minimum, see, the minimum distance is the perpendicular. We already have, but we will put that condition. We will put that condition that we want the x vector to be perpendicular to the y cap. Do we want this condition? This is also x vector, another x vector. Is it perpendicular to y cap? No. So we don't want this condition. If we take this condition, then your regression line is not the best fit. Because there is more error. The distance between y and y cap is high. Therefore, we will not take this. Will we take this distance? No, because the distance between y and y cap is high. So we will take a distance which is minimum. And what is the minimum among all these distances? Perpendicular distance. So we have to put another condition to say that that x vector is perpendicular to the estimation function y cap. So how can you put that perpendicular condition is I am asking. How can you think about it? This condition you tell, then only we will proceed. Hmm? What can we do? Yes. How can you devise that? I am just asking a simple thing. You have to set the x vector, that is the perpendicular distance, to y cap. What condition can we write? Huh? Very easy condition. If two vectors are perpendicular, what you do? Huh? Two vectors are perpendicular, what you do? Pythagoras. I'm not talking about okay. If by applying Pythagoras theorem, what you will achieve? Distance. Are we interested in computing the distance of y? By getting the distance, what do you do? We are not interested in that. We are interested in better prediction, better estimation. We want y and y cap to be close. Yes. Top product. Finish. This. This everyone should think. These are the opportunities which we give you in class to sharpen your brain, to think more. These you cannot say that you just teach us and that's no. We have to think. Okay. Now we know x is perpendicular to y cap. So the dot product will be 0. Okay. The dot product will be 0. So if the dot product is 0, so we will write that implies dot product of yes y cap minus y and y cap equal to 0. Right? Agree? But here is a catch. Here y and y cap are matrices also. Here y and y cap are matrices also. I mean column vectors. Right? So here it just won't be like dot product. So I will tell you one thing before we dive in there. Try to take it importantly, okay? So you understood the catch here, no? This is the catch, okay? Let us take two vectors. Let V and W be in Rn. There are two column vectors. Then I am telling you that V transpose W is nothing but the dot product. V transpose W is nothing but the dot product. Okay. Can we try that? Okay, let us try. So suppose you have, I don't know, maybe you can tell V equal to V1, V2, V3, so on, and W equal to W1, W2, W3, so on. Okay. So then we can write V transpose W as V1 up to Vn, and W is W1, W2 up to Wn. Sorry, I did not define. V is a column vector, that is V1, V2, so on up to Vn, and W is another column vector, W1, W2, so on up to Wn. Do you agree? These are the two column vectors. Okay. Now, if I take dot product, what is the dot product? You want V1 to be multiplied by W1 and V2 to be multiplied by W2, right? So you should get the dot product as V1 W1 plus V2 W2 so on Vn Wn. Do you agree? Right. Now, this is okay, you know about it. But what is V transpose W? V transpose will become a row vector, right? And W is also a column vector. So what you will do? You will multiply this with this. So what you will get? It is a number, no? It is a number. So what is the number? V1 W1 plus V2 W2. So on Vn Wn. So can you see that both of them are equal? Both of them are equal. So therefore, what you conclude? You conclude V transpose W is nothing but the dot product. Okay. The same case applies to us also. The same case applies to us also. Here Y and Y cap are the column vectors, right? Here Y and Y cap are the column vectors. So what you should do? Here what we should write then? After you understood this fact, the dot product of Y cap minus Y and Y cap equal to 0. So what we should write? This implies Y cap transpose times Y cap minus Y is equal to 0. Isn't it? Just apply this concept, what we learned over here, to here. Do you agree? I hope that is okay. See, slowly we are arriving at a condition. I mean, what condition to put so that you will get the best fit? Agree. Now we have to solve this equation. Okay. Now we have to solve this equation. So let us be back. Okay. So let me write here Y cap transpose Y cap minus Y equal to 0. Okay. What is Y cap? Y cap equal to, yes, Y cap, but we have Y cap equals to A beta, right? Can we substitute that? So what will be Y cap transpose? A beta transpose. So what is A beta transpose? You have two matrices A, B, and you are taking the transpose. What is it? Yes, B transpose, A transpose. So can we apply it here? Beta transpose, A transpose. So can we write here in the first equation, can we substitute? So beta transpose, A transpose times A beta, okay, minus Y equal to 0. Agree. Can we solve it? Can you solve it? What else you will get? Beta transpose A transpose A beta minus beta transpose A transpose Y equal to 0. Can I take beta transpose common? Beta transpose common if I take, I will get A transpose A beta minus A transpose Y equal to 0. Now multiplication of these are 0. What you will get? Either beta can be 0, which is not at all useful. Beta equal to 0 means it is telling you all the coefficient are 0, which we don't want. Okay, which you don't want. So what you want? So beta equal to 0 is a trivial solution. Is a trivial solution and not useful. So we have to take, that implies A transpose A beta minus A transpose Y equal to 0. Agree. Can we do something to it? What else can we do? But what is our aim? But while doing the calculation, we should know our aim. What should be our aim? By putting the perpendicular condition, we want to find the regression coefficients. What are the regression coefficients? Beta I, alpha 1, alpha 2, alpha 3 up to alpha n. Those are our regression coefficient, right? Basis function we know. We know the basis function. Our whole regression idea yesterday also was to find W, not W1. regression coefficients. We wanted to find W0, W1. Today we are going to find all regression coefficients. Alpha 1, alpha 2, so on. But alpha 1, alpha 2, alpha m or n are packed in the vector beta. We have to find vector beta now. So can we find the vector beta from this? So what we can do, we can write A transpose A beta equal to A transpose Y. So therefore beta is equal to, we can take the inverse, left inverse. So A transpose A whole inverse A transpose Y. Now this guy is something very interesting. This guy is something very interesting here. What you got? So you got a formula. Yes, you got actually a formula for your regression coefficients. Any issues? You cancel. Then what you get? Then you are getting y equal to a beta. But is it useful? Can we think? If can we do like that? If we do like that, what else we get? Can we think about it? No, it's a correct option. Like you can go through that. But if we do that, where we might have some issues. That's what I'm asking. That you have to think. You let me know next class. Next class you should tell me. Anyway, so we wrote it as equality. Okay, and we are writing now beta equal to A transpose A whole inverse A transpose Y. Okay, now this is very interesting. Okay, why it is interesting? Can you tell me the A matrix? A matrix was a M cross N matrix. A matrix was a M cross N matrix. That means it is not a square matrix. No? Might not be a square matrix. I mean, can be a square, but not always. But it's a rectangular matrix. A M cross N is a rectangular matrix. So what I wanted to convey to the class is there are many methods in this semester and previous semesters, and also in machine learning course. You will see many algorithms always depend on square matrices. Always, most of the time till now in your career, you might be seeing that let us consider A to be a square matrix, and then only you can compute the determinant. Then only you can compute, yes, then only you can compute the inverse. Okay, but now here the matrix A can be a rectangular matrix. The matrix A can be a square matrix, whichever, but this method is going to work. That is the power of this method. It doesn't want your matrix A to be very nice square. This method can work for a square matrix. This method can work for a rectangular matrix also. Because already in your start case, you already told matrix A can be a M cross N matrix. What you need here? You need A transpose A to be invertible. Here you need A transpose A to be invertible. Then only this inverse can exist, and then only you can obtain beta. But if your A transpose A is not invertible, the method might fail. The method might fail when A transpose A is not invertible. It is not necessary for A to be invertible, but it is necessary for A transpose A matrix to be invertible. And this, what is the power of this method? It can work for any matrix A. Whatever dimension of data, how many basis functions, doesn't matter, but this will work. So it gave you a very nice equation to obtain the regression coefficient beta. Beta is what you want, no? This shows that your regression problem is solved now. And this is the best fit. This is the best fit. Why? Because you already saw the regression line and the given data set line can only be closed at the perpendicular distance. And you to put the perpendicular condition and then obtain this beta. So that this beta already incorporates the best fit. inside it. So this is the best fit you can get. And if you take these beta coefficients, then only you can get the best fit. Any other beta coefficient you get won't get the best fit. Can you see the importance of this method? So this is why I derived it for you. If I just wrote this formula, then why you will believe, isn't it? We derived geometrically, and we used linear algebra to come to a conclusion how regression works here. Okay. Now this is something very nice. Okay. And this is something very interesting, and this is known as it deserves a name. Okay, Murray and Penrose devised this method, and it is a Murray-Penrose generalized inverse. Murray-Penrose generalized inverse, and I am sure that you will come through these inverses at many places. At many places. I feel like those who are working in RC might already have seen this kind of inverse. Okay, might not be exactly this, but it will be a combination I plus A transpose A something. Okay, so it's a generalized inverse, and it is so important that Python has already kept a predefined function for it. You can achieve pseudo inverse of a matrix A by using pinva command in Python. Pinv command, if you ask in Python, it can give you the pseudo inverse of a matrix A. The matrix A, pseudo inverse of a matrix A need not need A to be a square matrix. A can be a rectangular matrix, and you can find a pseudo inverse. So if a question comes, can you find pseudo inverse of a rectangular matrix? Yes, no. What you will do? Yes, we can find pseudo inverse of a rectangular matrix. Okay, you got that right. Okay, we'll see that in Python also. Okay. So, so A transpose A inverse. A transpose A whole inverse A transpose is known as the pseudo inverse of A. Okay, and it exists. Okay, if A transpose A is invertible. That is natural, no? Because you are using the inverse. So the inverse should exist for the formula to work. If the inverse doesn't exist, it won't work. As simple as it is, common sense. I mean. Okay. So what we have learned so far, we'll come back again before we go to the problem. I will give you a problem here. Actually, we will do two kind of problem today. Okay, we will use least square problem first, and then we will go back to another. We'll solve two different problems. One problem we will solve in the class for least square regression, and another problem we will solve in the class for pseudo inverse. Okay, and then the third part is we will look into various Python codes. We'll look into various Python codes. Okay. So that's what we are planning to do now. Okay. Okay. So maybe we'll do a problem now. We'll do a simple problem first. So now we'll do some practice. Okay. So this one, you just keep in mind that we can obtain beta by using A transpose A inverse A transpose Y. Okay. A you know. Okay. A you know. A transpose you know. Y you already know given data set. So beta you can always obtain. No issues. Okay. So given a problem, you can always work it out. Okay. So we will do a problem later, but first we will do a problem on least square. Okay. So let us do this problem. So I will give you two data sets. Like maybe have you seen camphor? mean, this comes from a data set, small data set, not a big data set, but from a chemical background. Okay. Just to give you a perspective of how other people or chemical engineering people or other scientists, they are using regression in their everyday experiments. Okay. So how many of you have seen camphor? Camphor. Camphor. Camphor, that white one. Good smell comes. Okay. Many colors it is available. Green, red, white. You just throw in house. Okay. Camphor. Now, what is the property of camphor? What is the property of camphor? The mass decreases. It sublimes. After 10-15 days, you will see that it is not there. After 10-15 days, you will see that the camphor is not there. Why? Because it sublimes. It gets sublimation. Go back to your class 6th, 7th days. Okay, sublimation process. Okay, okay, fine. That is one case. Now let us come back to another case. You know, salt like powder, like grains, right? Grainy kind of. But you have salt which look like rock also. Okay, you keep that salt here and go. After like tomorrow you come back, what you will see to that salt has happened. Open it, you keep it open. It will absorb water. It will absorb water, right? That's the property of salt. It absorbs water. If you keep some salt powder on your table and come back tomorrow in your kitchen, it will be watery. It will absorb water. Okay. By absorbing water, what happens? The mass of the salt increases. Don't you agree? Yes, sir. So how much? So if the salt is good, it will absorb water. Yes, sir. If your salt is not good, it will not absorb water. So how much the salt has absorbed water? How will you know? So there is a food scientist. This is where you can apply statistical analysis and data science to food tech. These are some examples. For example, I went to a food industry. Okay, it is Fonterra. There is a food industry in New Zealand. It is known as Fonterra, and what they do is they have cheese. They are a big company which take milk and they do all dairy products. So one half is going to milk, another half is going to making cheese, another one is going to make something like other dairy products, something. So they had a problem that our cheese, what we are making, is not homogeneous. The cheese they make in the company or in the industry, it is not homogeneous. How can we make it homogeneous? That was the problem. Can you use data analytics or data science applications to make the cheese homogeneous? How they found the cheese is not homogeneous, you know? One guy purchased one block of cheese and the person ate the front part of the cheese. He is not getting that much taste. But when he finishes the cheese towards the end part, he started getting more taste. So the front part is having less taste as compared to the end part of the cheese block. So therefore, through that, you can see that cheese, the homogeneous property is not there. They wanted to do the cheese in such a way that it is homogeneous. Okay, so how you can do? So we used Raman spectroscopy. Okay, we use Raman spectroscopy for that, and we got the spectroscopy data of the cheese, and it was a very noisy data. So you have to handle the outliers and all those things, and we were working on it. Okay, and it is a very industrial problem. I mean, you can apply some sort of techniques which you learned in data analysis, like outliers, noisy data, binning, and all those things there. And it was following some distribution. If the cheese is uniform, it should be a very uniform distribution in any direction you take. But it was following some distribution. It was not linear. We found that. So therefore, their cheese was not uniform. Our idea was to make that distribution turn out to be uniform. Okay. So it was very difficult, but that's how people collaborate. Okay. So this is another example, small example, to know whether in salt industry, for example, I don't want to name, but any other salt industry, whether your salt is of good quality. How will you know that the salt is of good quality? If your salt doesn't absorb that much water, there is a guidelines in FSSAI, food industry guidelines, that 10 gram of salt should absorb X gram of water. If it absorbs that way, then only the salt is of good quality. If it doesn't absorb water that way, it is not of good quality. How will you test whether your salt has iodine or not? One simple test is sprinkle some lemon on the top, like then if it turns bluish and all, it has iodine. And actually some salt are having the quantity of iodine. If the salt doesn't have that, it will not turn, it will be white, right? So these are some tests. So how will you know that much? You have to do experiments, no? You have to do experiments, right? You will take 10 gram of salt and see after how much time, how much water content it has done. Okay. So you will see what here, with the increase in time, the amount of the weight or the mass of the salt is decreasing or increasing. Huh? How many of you think decreasing? Decreasing, how many of you think? Increasing, how many of you think? Yes. Decreasing or increasing? Huh? It should increase, right? So that is the problem here. Okay, so with just giving the data set, I thought of giving some background of what is going to come. So that's the same data set we look into here. Okay, so this is the data set you have, time and mass. Okay, this is X and this is Y. Okay, so suppose you have at time t equal to 5, okay, units. I mean, it can be 5 minutes or it can be 5 seconds or it can be 5 hours. That we are not looking here. That you can look later. But our idea is to have a practice of least square regression. So 5, if the time is 5 units, then the mass was 40 grams. When the time was 7 units, the mass was tripled, 120 grams. Okay. It is some super salt. It is a super salt. It is absorbing water like anything. So if the time, suppose is 12, it turned to 180. 16, it turned to 210. 20 to 40. Okay. Now the question is, okay. Now the question is, compute the regression line. Given this data set, find the regression line which can best fit this data. Find the regression line which can best fit this data. This is a small data set because you can just use your notebook to solve it. But in realistic, you will get 10,000s and or 20,000s of data set that you can use Python to do that. We will see that also in Python. We will take 1,000 data sets and how using LSTSQ. You don't have to write any formula here. In Python, you have to just do LSTSQ and give the data set. Give the data set X and Y data. Okay, and it will the output will be the regression coefficient W0 and W1. Finish. Just one line in Python can solve you this. But however, we want you to know how to compute the regression line using the covariance and the variance. Okay, yesterday concept. Can you compute? Can you compute that? So what is our y cap? Y cap, you have to find W0 plus W1x. What is W1? W1 is the covariance of x and y divided by the variance of x. And W0 is equal to? W0 is equal to? Yes, y, mean of y minus W1 of x bar. So can you compute this and tell me what is W0 and W1 for this case? Right. So continue. Tell me the data points. Tell me the data points. So xi is 5 and yi is 40. So x bar you got what? X bar is the mean and it will come to 12. Y bar? Yes, correct. Okay. Now xi minus x bar minus 7. Okay. Yi minus y bar minus 118. Then xi minus x bar into yi minus y bar. This into this, -7 into -118, it is plus 826. Xi minus x bar square, this is square, -7 square, 49. Next data point, 12, sorry, 7. 7, you will get 120, then -5. Yes, this is -38. This is, yes, then, yes. Then the next data point, 12, 180, 0, then 22, yes, yes, yes. Then 16, 16, no? 210, then 4, then, yes, yes, yes. Then, mm-hmm, 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 mm-hmm. Exactly 64. Yes. Now what we can do? Now can we take, now fxy is what? Yes. So W1, can we find W1 now? So W1 is equal to Sxy divided by Sx. So that is equal to summation of xi minus x bar into yi minus y bar divided by summation of xi minus x bar whole square. Exactly. So what you have to do now is nothing but I will tell you why this is important. Sum them up. Sum all of this and divided by sum of all of this. That's it. That's it. So can you sum them up? Where it went? So what do you get? 1880 divided by 154, and this comes to be something. Okay. So this is W1. Can you compute W0? W0 is nothing but, yes, W0 is nothing but y bar minus W1 x bar. That is equal to y bar, you already found out 158. Minus W1 is 12.208 into x bar, that is 12. So you will get it around 0.6, right? 3 decimal points. So your equation of regression line therefore is, equation of regression line is therefore, yes, y cap equal to W0. What is W0? 11.506 plus W1. What is W1? 12.208x. So this is your regression line. This is your regression line. Now, can I ask you the question that estimate the mass, okay, at time t or x, time is x, no? At x equals to 14 units. Then what's the mass? Y cap is the mass. So y cap, that is mass, is equal to 11.506, and at time t equal to 14 units or x equal to 14 units is nothing but 11.506 plus 12.208 into 14. So what is this value? Where is that? Why can't you use that? Hmm? 182. Exactly. 182.18. Okay. So can you see that in between 12 and 16, 180. At 12 it was 180, at 16 it is 210. And this value which you estimated at 14, time t equal to 14 units, and time t equal to 14 units is lying somewhere in between 12 and 16. So, and the weight is also lying in between 180 and 210. That is 182. So this is something like a intuitive way. I mean, the weight if comes out to be 500, then you will see something unusual happened here. Okay, but the weight remained nearly 182, in between 180 and 210. So you understood what I'm trying to intuitively tell you. Got the idea? Good. So similarly, we'll give you assignments. Okay, we'll give you assignments like I think MCQ would be good. We'll give you MCQ assignments similar like you are getting in test, so that you can practice this again and again. Good. So one example we'll do, and the rest you can cover in your uh, assignments. Okay. Now let us do another example for pseudo inverse. Let us do one example for pseudo inverse. So how we should do this? Pseudo inverse. Okay. Okay. Consider a situation. So it's a very interesting problem. I want everyone to, enjoy this problem. Okay. Because it is fun also. So consider a situation. Okay. Consider a situation consider a situation where there are two features. Okay. Consider a situation where there are two features and I am naming them as x1 and x2. Okay. And a target variable and a target variable y and a target variable y. Okay. And these can be I mean, what are these variables? So it is written next. These can be hours you spend on Instagram. Okay. Instagram per day. Okay. Comma per hours on TikTok. Okay. And the level of brain rot you experience. Okay. So this is a problem with data. I mean, you can do this data. Okay. Unfortunately, one student is missing who does that. Okay. Later, we'll discuss that. Okay, fine. So we'll have some data here. We'll have some data written here. Okay. So Instagram. Okay, Instagram. This is x1. I mean hours. What? Instagram. Okay. Then TikTok, suppose. Okay. And this is also hours, but we are measuring by x2. And based on these two features, there can be more, but for simplicity, we are doing these two features. Okay. Instagram, how many hours are you using? X1 hours. And TikTok hours, you are using X2 hours. And our aim is to understand the brain rot. Okay, that is happening, and that is known as Y. We want to estimate the amount of brain rot depending on these data sets X1 and X2. Okay. Now we will write down the data. So when you experience 2 hours of Instagram and 4 hours of TikTok, you get the brain rot of 29 units. When you use 5 hours of this, one of this, you are getting 15. Okay. When you get 3, you get 24. Okay. When you get 4, 3, you get 27. When you get 2, 5, you get 34. Okay. We want to find, our aim is, okay, what is our aim? Our aim is to find the relationship between x1, x2, and y. This is our aim, isn't it? I mean, how much brain rot occurs depending on the amount of hours spent on Instagram and amount of hours spent on TikTok. Okay. And we are thinking that we can do a linear relationship like for the regression line. So what we will do is we can estimate our y cap, that is the estimation function, as some constant theta naught plus theta 1 x1 plus some theta 2 x2. I mean, this is our first choice. This is our first choice. Okay, linear regression. If it doesn't work, doesn't work, but this is our first choice, a linear regression. Okay, but here what you see, here something different is there. Previously, when y was depending on a single variable, y equal to w0 plus w1 x was the only feature. But now here you have two features. x1 and x2. So therefore, what we are doing, our estimation function is written as theta naught plus theta 1 x1 plus theta 2 x2. Here, what is our basis function? x1, x2. What is our regression coefficients? Alpha i's are like theta naughts. Theta naught, theta 1, theta 2. Can you see we have written as a linear combination? Can you see whatever we have learned is now coming into action? Okay. Now you will see we can use pseudo inverse concept here. Okay. Such that error between y and y cap is minimized. Agree. Okay. So let us start. So again, for this problem, we have to set up as how we can set up. Can you tell me what should be our first thing? Huh? A and yeah. So which one is A here? What is A here? What is A here? Can you identify what we are trying to find? Can you write it in terms of that pseudo inverse we discussed in class? I mean, first you have a try, then we will start. You understood? I mean, what you have to find? You have to find actually theta naught, theta 1, theta 2. That is your aim. How you that so that is like a beta to you. That is like the beta vector. That is like a beta vector, right? So how you can write it as y cap equals to a beta, and then how you can find beta? Beta equal to A transpose A whole inverse A transpose Y, right? So Y you already have. Y is what? Y is 29, 15, 24, 27, 34. What is A? If you can find A, directly substitute that inverse and compute it, beta. So directly within one step, you will get theta naught, theta 1, theta 2. So can you make some relation? A is nothing but the collection of basis functions. Basis functions, but not only functions, functions evaluated at the points. So that is nothing but x1, x2 here. That is nothing but x1, x2 here. Isn't it? Yes or no? So how many data points we have? Here A is A we want to find. A was a M cross N matrix. M was the number of data points. How many data points you have here? 5. N is the number of basis functions. How many basis functions we have? X1, x2, 2. So A should be a 5 rows and 2 column matrix. That's how you do this. This is the catch. How you implement the theory into problem. So therefore, your A matrix is not a square matrix. It is a rectangular matrix and it is this matrix. Okay. What is the Y matrix? Y matrix is nothing but 29, 15, 24, 27, 34. Okay. So what you need to perform? You need to say beta, which is a collection of theta naught, theta 1, theta 2, is nothing but A transpose A whole inverse A transpose Y. So what you have to do, you have to find A transpose. If A is this, A transpose is equal to 2, 5, 3, 4, 2, then 4, 1, 3, 3, 5. So can we compute A transpose A? What is A transpose A? A transpose A is nothing but the multiplication of these matrices. So this is a 2 rows and 5 columns, and this is 5 rows and 2 columns. So finally you will get a 2 by 2 matrix, isn't it? 2 by 2 matrix. So what is a 2 by 2 matrix? So this is a catch. This problem might come. This kind of problem might come. So therefore I suggest that everyone should know how to do matrix multiplication in your scientific calculator. How to compute inverse. See, suppose you did not use calculator. Okay. Then this is a 2 by 2 matrix. So you have to find the inverse of it also. So you have to be ready. So if you do that, okay. So basically you compute the pseudo inverse first, PINVA in Python, and just multiply with the y vector. Okay. So tell me how much you are getting. Okay, another important thing here, why someone missed, most of us missed. Okay, and only one of them asked. Okay, is why here in this line you can take A transpose common, and then you will get A beta equal to y, and then solve beta. Finish. Why we are taking pseudo inverse and all these things? Our final aim is to find beta only, no? Here you can take A transpose to be common, isn't it? Yes or no? A transpose is here, A transpose is here. Take common. A transpose cannot be 0. So y equal to A beta. And take the inverse. Okay. And take the inverse and get beta, no? How many of you think correct? You cannot do that. Why? Because A is a rectangular matrix. A is a rectangular matrix. That is the catch of this whole process. You cannot take the inverse, so you cannot get beta. You can still get beta by solving the system of linear equation, but if your data set is too high, solving that linear equation is itself a high process, computationally expensive. Therefore, by multiplying this A transpose is able to solve you a lot of things. That is the catch here. Okay, therefore this method is known as the pseudo inverse method of regression. Okay, you understood the catch. Okay, this is your assignment. We'll move to the Python aspects now. Okay, quickly we'll move into the Python aspects. It is the last one. For nonlinear functions, I mean, if you have, I mean, this is known as least square regression. Least square regression for nonlinear function. Least square regression for nonlinear function. Okay, I mean, if your function is nonlinear, then how you are going to attack the regression problem? Okay, that is the catch here. Actually, there are some functions which you cannot put into the form of the basis. Okay, where but least square regression will still be appropriate in those cases. Okay. So the idea is, if you have a nonlinear function, try to use some transformation to make it a linear function. Like if you have e to the power x, apply log, then it becomes x. Like the techniques. I mean, there are some techniques, tricks. Okay, we will see the tricks. So one of them is log tricks. Okay, the whole idea is apply some transformation, apply some transformation to make the nonlinear function, okay, to make the nonlinear function transform to a linear. That is the idea. So let us see log tricks. Okay, log tricks. Okay. So for exponential function, you can apply this log tricks if you have a data set which the data are spread in an exponential way. I told you that day. Here. The data is following an exponential trajectory, right? Exponential way. You cannot just take the linear. Okay. So you have to use this log tricks usually applied for exponential functions. Okay. For exponential functions. And how we do that? Suppose you have the estimation function as this one. And what is your job? Your job is to compute. Your aim is to compute alpha and beta. Your aim is to compute alpha and beta. Okay. So y cap x is alpha e to the power beta x. Okay. And you want to use least square regression to find and compute the values of alpha and beta, because after doing that, you can get the regression line. The estimation function you can get, isn't it? That's the idea. Okay. Okay. So what to do here is, in order to still use the least square regression idea, take log on both sides. So if you take log on both sides, so log of y hat x is equal to log alpha plus beta x, isn't it? Don't you agree? Yeah. So you can write, okay, you can write this as y tilde of x. Okay, log alpha you can write as some alpha tilde, and beta x maybe you can write beta x. Then this guy turned out to be y hat of x, or y tilde of x is equal to alpha tilde plus beta x, isn't it? So are you able to understand how we converted this problem, which is exponential fitting, into a least square regression form? Are you able to understand? No? How many of you did not understand? No, see, you have a data. These are the data points. These are the data points, right? Now the question is, you cannot fit this with a straight line. It's not a good ideal fit. So therefore, what you think is, yes, this data is behaving in an exponential way. So therefore, let me fit the data using an exponential function. So therefore, my estimation function I wrote as sum alpha times e to the power exponential beta x. Right. Now, if I can find what values and alpha and beta I can take so that it can best fit this data, then I will get the regression curve estimation function, isn't it? You understood? But we don't have any method developed yet to compute alpha and beta unless it is a linear function, right? So therefore, what we can do is convert this into a linear, apply some transformation to convert this to a linear form. This is what I told here. Apply some transformation to make the non-linear into a linear case, isn't it? So what we did, we apply log on both sides. If you apply log on both sides, what you are getting? If you apply log here, log y tilde, apply log alpha plus beta x, right? That same thing I am calling this log y hat as y tilde of x. And this beta x is beta x, log alpha is still a constant only. So I'm calling it alpha tilde. So you can write this form into this, that is y hat or y tilde of x is alpha tilde plus beta x, right? So now you can solve for this. No? I mean, you are converting that exponential fitting into a least square problem. That's the whole catch. Now you can only compute these values, alpha tilde and beta, frame it as a regression problem, least square regression problem, and try to compute the covariance and try to obtain all the values. Now okay. Now is it okay for everyone? Okay. I mean, okay. Now we cannot do much about this. We have to see Python. Let us see Python, okay? How different kind of regression it is trying to fit. I will show you why this method works. Why this method works, okay? Okay, let us go through these. Is it clear till last time? Visible, no? Okay. So what we are doing here is same, least square regression. Okay. You see X and Y, there are a lot of data sets. If this many data set, it is very hard to do by your calculators and all. Okay. So what I am doing here, same thing. X bar. X bar is the np dot sum divided by n. That is like the mean. Y bar. Okay. XY bar, X2 bar. And you are computing W1 and W0. You are computing W0 and W1. Okay, you know that how you are getting the intuition, no, what you did in your notebook and what we are writing in the code. Hmm? Okay, fine. So what we are doing here, you can see I am plotting the X and Y data. Okay, these are the blue points, and this is the orange line is the regression line. That is the Y hat equal to W0 plus W1x. And I am printing the W0 and W1x here. So W0 is 17.93 and W1 is minus 0.25. Can you see why the line has come like this? Can you tell me? If you have this curve, very interesting problem. If, if you have this X and Y data sets all distributed and your regression line is coming like this, but what I am asking is why your regression line is like this, but not like this one, but not like this one. Hmm? From the regression curve itself, you will know that. Here, W0 plus W1x. What is W1? It acts like a slope. W1x, mx plus c. W1 acts like a slope. And W1 is negative here. Slope is negative. So it cannot make an acute angle. It has to make an obtuse angle. Are you able to match things? So there are many different ways to see the same thing. This is what I want from you guys. Okay. So now you understood why your regression line is like this, but not in any other shape, right? So intuitively you can think because W1 is negative, so it like represents the slope, so it has to make obtuse angle. Got the idea? Okay. Now let us come to the Penrose generalized inverse, okay, where we have taken this A transpose A inverse A transpose, okay. Here we are just giving you one example, like you can see A1 is your matrix. I mean, not exactly the problem I gave, but you can use this problem given to you into and put this into the code and try to formulate that and get what you are getting. Okay. A is same, the basis functions. Okay. The first column is the first basis function. The second column is the second basis function. Okay. Fine. And this is your the B part. B part means the Y part, given data. Y is a function of x1, x2. These are x1 and x2, x1, x2. This is the Y. This is the Y. Okay. What you are doing? You are computing the pseudo inverse here. np.linalg. You have to use that package here. .inv. Okay. So you are taking A transpose A inverse, no? You are taking inverse of what? Yes, that's what is happening. A transpose at the rate A. Multiplication has happened and you are taking the inverse of this. After that, what you are doing? Multiplying by A transpose, right? Yes, you are multiplying by A transpose here. So print the pseudo inverse of A. Okay. So this is the pseudo inverse you are getting. This is the pseudo inverse you are getting. Okay. What I suggest you guys, I have submitted this code to you. Try to put the values you have in your problem into this code and get the pseudo inverse. Get the pseudo inverse. Okay. Then what I am doing here now, I am multiplying with y. Y is nothing but b here. So you are getting x, three values. Try to check why not. Why here you are getting but there not. See, therefore I did not answer one of her questions. And I then spoke about why there is a catch. So where is the catch? If you dig into that, only then you will understand. Okay. No. You will get it. One step you will get the correct answer. You don't need any random guess here. No guess is working. Yes. What is that column should be? Do we have that? Then how can we get? I mean, I showed you clearly here what is happening here. You understand this code first. Yes. Yes. Some catches there. So this is what I want you to do the assignment. This is why I gave you the assignment. So that you go and see where you missed things. But yeah, very, very near. Almost near. Almost near. Okay. That's what is done here, no? If you understand this part, you will understand all the things. Yes. Yes. Okay. But why we need that? That's my concern. Why you will add that? I mean, the problem it is not coming. So why you will need to add once? That I want you to think. Yes, because theta naught is multiplied by 1. Others are multiplied by x1, x2, no? You have theta naught times 1 plus theta 1 times x1 plus theta 2 times x2. So the basis functions are 1, x1, x2. You are doing only x1, x2. You are missing ones. That's the catch. This is where we give the assignment to understand where you are missing the important parts. But anyway, it is all revealed now. So x equal to A inverse, the pseudo inverse B. Okay, you understood why you are getting. So these are your coefficients. Theta naught, theta 1, theta 2. Your regression curve is finished. Simple as that. Okay. Anyway, so NumPy provides us with a function. Okay, now this lecture, the remaining part of the lecture will deal with whatever methods you have learned mathematically and in your notebooks you did all computations. We want to show you that all of this you can just do it with one line Python code. Okay. So finally, the main intention was to make you understand all the inner working mechanisms before turning out into the Python code. So NumPy provides us with a function for computing the pseudo inverse. As I have already mentioned, this is known as .pinv function. Okay, pinv. Okay, pinv of A. If you give, the output will be A transpose A whole inverse A transpose. It will already do inside and give you. So for example, x is equal to np.linalg.p in A at the rate B. So this, oh sorry, where? Yes. So this is already computing the pseudo inverse to you. And that you are multiplying with y. Y is nothing but B here. You got the idea. So the same answer you are getting, no? See, here I did not apply the pseudo inverse function. Did I apply pseudo inverse function here? No, I applied just inv function, okay, which is already there, okay. And then I did the calculation. I got the answer coefficient as minus 1.4, 2.1, 6.4. Now, instead of these lines, this big confusing line, I can just do PINVA. And within that, I got the same answer. Compare this answer with this answer. The same answer you are getting. Can you understand now? So with just one line, you can get your regression formula. You don't have to do a lot of steps. That's the computational power. Okay. Okay. This I want to do. This we can. Huh? Okay. This are all same. Huh. Another idea is you can use least square function. Okay. I mean, just give the for a least square what you want. X dataset, Y dataset, and then say y cap equal to w naught plus w1x, isn't it? All that thing, but that w naught w1, how are you computing? Covariance of xy divided by variance of x, right? Yes, yes, but that is very computationally expensive also. You have to make a lot of computations and all. So what Python did is he has a LST-SQ function where you just give the data set A, Y, that's it. No conditions here, but R cont equal to none. You can give some conditions. You can explore what these are. However, I have not touched this part. R cont equal to none. You can see what else can you, what additional feature you can make. Okay. But A, Y and just print theta. W naught W1. So the output is here. W naught W1. Are you getting? I mean, now we are able to see, right, the computational efficiency and all powers Python has. Just with one command, you can get these things. LST, so by far what you done? PINV, LSTSQ functions in Python, which can do regression for you. Okay. Now there is another concept that is curve fit. Okay. I mean, for all the things what we are doing is fitting a curve. Okay. We are doing a fitting curve. Okay. Use optimized.curve fit from SciPy. Till now you were using NumPy. Now you can use SciPy package also. Okay. So this SciPy function is actually very powerful that it can fit not only linear functions. Yeah. Yeah. Least square. LST SQ. Least LST least SQ for square. Okay. It can not only fit linear function but many different function forms such as nonlinear also. Here we do not need to turn y into a column vector. Okay. Here you don't need to do any vector operations. Okay. Just call the function curve fit. It will do the remaining part. It will try to optimize. It will try to optimize in a way that you get the best fit. Therefore, it is we are calling like optimized.curve fit. It is using some optimization algorithms in the backend, which you are not seeing. So here what you need to do, you tell that yes, I need in the form of ax plus b, the estimation function, I need a linear in the form ax plus b. Okay. And then just use the x data and the y data. So func, what input it takes? It takes three input. The estimation function, the x data, the y data. Okay. Finish. Then just print that. Okay. See, you are almost, I mean, there is a difference, I think, right? There is a difference between the two. This gives you 1.519, 0.975, but curve fit gives you 1.585 and 0.97. I mean, W1 is very close, but W0 is not that close. Almost close, but it is 1.51, here it is 1.58. Some difference, not exact same. Okay, means different method is giving you different regression lines, but almost similar. I mean 1.5. Just the change occurs in 0.01 accuracy, 10 to a minus 2 accuracy, second decimal place. Yeah. I'm just giving you this idea. You can later look into this very carefully. I'm going through this so that you can just go inside and look into each of this carefully. The log trick I mentioned in class. If you have exponential data set, can we construct exponential data set? Yes. Here I am constructing. This is synthetic data. It's a synthetic data. 0.1 np.exp 0.3x, and then I am using some random values. Okay. So, but what will happen? It will be if you just use exponential data, It will just come like this only, no? That we don't want. We need to add some randomness to it. So the data will spread in a random way, but still follow the exponential path. Therefore, there is some deviation here. Are you getting the idea? So how the data set looks like this? You got it, no? Exponential function we gave, but some randomness we added. Therefore, it is not in a curve. It is spread out nearby that. Means it is not a curve like this, but it is spread out in top, bottom like that. Now the question is fit this. Fit a regression curve or fit your estimation function here. Fit your estimation function here. Okay. How you will do? You can use the log trick. Okay. Let us look into two things. Okay. You can use the log trick also. Can you look into the log formula actually? So here we have used least square, LSTSQ. Am I clear to audience or? Hmm? Oh. But this part, if we can see through, it will be good. Else we have to start in a new session. What do you want? Huh? Okay. Okay, good. So you have this. Only there were 2, 3 things only. But anyway, only there were 2, 3 things. Fine. We'll do that next class. Hmm?